Hi everyone, I am Alex Converse. I'm a video engineer at Twitch, and I'm going to be speaking tonight about the internals of the SRT protocol. I've seen a lot of great talks about all the cool software that supports SRT and all the neat things you can do with it, but I haven't seen too much that really peels back the curtains and shows what's going on underneath. So I'm going to try to demonstrate some of that. A few disclaimers real quick. These opinions tonight are mine only. They're not Twitch's or AWS's or Amazon's. But at the same time, if you find this stuff interesting, Twitch is hiring. I'm not part of the SRT Alliance or any sort of like official spokesperson for SRT. I just am the sort of person that finds this stuff really interesting. And I thought I would share it with you all. And you don't need anything that I am talking about here tonight to use SRT. They have a really great open source library that's really simple. I'm really trying to figure out more how it works and what kinds of weird things you can make it do. All right, so with that, what is SRT? Well, SRT is obviously a subtitle format, but this is a different SRT. This is a video streaming transport protocol. It is designed for streaming live video over challenging networks. It's UDP based. It is one-to-one. It's focused on contribution, not on delivery. It offers sub-second tunable constant latency. That's kind of a lot all in one sentence. Sub-second, pretty straightforward, less than 1 second. Tunable, you can configure the protocol. You can adjust the latency that it offers to trade off versus packet loss, how much latency you want to tolerate versus how much packet loss. But once you start a broadcast, that latency is locked in, and it's not going to accumulate more latency because of things like network events. It also offers content encryption. So why do I think SRT is interesting? Well, RTMP is the de facto standard for live video on the public internet. It's been around for a long time, and it's been abandoned for a long time. It was abandoned by its creator. The last update was in 2012. There's no standard mappings for sort of modern codecs like HEVC or AV1. I mean, those things are actually kind of fixable if someone really wanted to stand behind it and fix those, but it has other problems. It doesn't work well on challenging networks, especially mobile networks. And SRT is one of several technologies positioned to replace it. Some of the others are RIST from the Video Services Forum and WebRTC. But in this talk, I'm going to be sort of going deep on SRT rather than going horizontal. SRT seems to have a lot of momentum these days. Walking around the South Hall at NAB, it seemed like every booth had an SRT Alliance member or an SRT Ready sticker on it. There's over 250 members in the SRT Alliance now. SRT works out of the box in VLC, in GStreamer, in FFmpeg, and there are some patches in progress for tools like OBS Studio. So SRT has its roots in a much older protocol, a protocol called UDT. UDT was created in 2001. You can tell it's old because its web page is on SourceForge. UDT was designed for transmitting large files quickly over public networks. And the UDT developers actually submitted several drafts to IETF on sort of the informational track describing how UDT works. And there were 4 drafts in all. The final draft was released in 2010. After the final draft, the lead UDT developer continued to work on the protocol for about 3 years. The final release was in 2013. So UDT is actually just as dead as RTMP. So Hivision, who is an encoder vendor largely, is what they're known for. They took UDT and they added features for this file protocol to turn it into a protocol that's friendly for live video. And they first demoed this at IBC in 2013. The main thing they were really trying to demo was like their HEVC encoder, and they were like, hey, we also got this thing for transmitting video over not so great networks like this show network, and it's built into our encoder, so you like get it for free if you're buying our HEVC encoder. And about 4 years later, they decided that maybe their own custom protocol wasn't a great way to create an interoperable ecosystem. So they released SRT open source in 2017. And they joined forces with Wowza to create the SRT Alliance to promote and further develop SRT. In early 2018, they released sort of the big 1.3 update to SRT. This is the biggest change to the protocol since the initial open source release. They changed the Mozilla public license, they add a new handshake, and they re-add file transfer mode, which they broke to create SRT in the first place. Later in 2018, they released something called the SRT Technical Overview, which is really like the SRT specification. It's 89 pages long. For comparison, the RTMP spec, I think, is 52 pages, and these pages are a lot denser in the SRT specs. There's really a lot more information there. It's a really detailed specification. Even people who are partisans of some of the competitors have admitted the SRT spec is really great. So at a high level, SRT uses a single bidirectional UDP socket. Data and control, they're flowing over the same socket. Without TCP, SRT is on its own for reliability, ordering, and congestion control. It uses selective retransmits for dealing with packet loss, and it offers what they call a unique encryption system built from standard primitives. It does not use DTLS. So the SRT data payload, it needs a payload that can be fragmented into small pieces. The protocol is technically agnostic, but in practice, I've only ever seen it used with MPEG transport stream. The whole transport stream packet goes in the SRT packet. Each transport stream packet has its own sync byte in there, the transport stream headers. I'm sure that sync byte is really useful in that third packet out of 7 where you're either getting them all or losing them all. I say out of 7 because in a 1500 byte MTU, if you're trying to pack in 188 byte packets, you can fit not quite 8. But that gives plenty of room for headers. Even with IPv6 headers and SRT headers, there's room if they ever wanted to add more headers. So this is the anatomy of an SRT data packet from the technical overview. At the very beginning, you have a UDP header, and then you have the UDT header, which has been adapted into an SRT header. And the first bit is 0, which indicates that it's a data packet. And then you have a packet sequence number. This starts from a random value determined during the handshake, and it increments by 1 for every packet. This is the number used to identify packets and packet acknowledgement and packet loss messages. So then there's a message number. It starts from 0. It also increments by 1 every message in live video, and it seems to be unused. And I'll get back to why I think that is in a minute. There is a timestamp in microseconds. This is the elapsed time on the sender, and it's used on the receiver for when to play this packet out of SRT's buffers into the TS demuxer and video decoders downstream. So we have these fragmentation and ordering flags, and they're always 110 for live video, and 11 means standalone. And the message number I think is really for packets fragmented across messages fragmented across multiple packets. But in live video mode, we just cram as many TS we can, and we call it a standalone message. So it's really for file transfer mode. The ordering flag just says it's OK to deliver this out of order if something has gone wrong. Then the following 2 flags are encryption and retransmit flags. The encryption flags tell you which key is being used, and the retransmit flag tells you if we're sending it the first time or sending it again. Retransmitted packets keep their original sequence number, their original message number, and their original timestamp. So if you're getting one of these later, it's useful to know that your clock hasn't gone wonky or anything. So the core idea in SRT is that the sender and the receiver both agree on latency buffer times, and they're trying to synchronize their contents by the time packets start flowing out of the receiver. VLC supports SRT out of the box. OBS has SRT in available in patches right now. These are both really cool open source projects. You probably use one or the other of them, maybe. If you do, maybe consider kicking them a couple dollars. They both accept donations. Anyway, done shilling for these guys. The sender creates a packet, and it sticks it in the latency buffer, and it sticks it in the network. And it's going to take a little while to arrive at the receiver. So the sender keeps generating packets. The receiver finally gets a packet. Sender keeps generating, receiver keeps receiving, sender keeps generating. Well, this is not good. Packet 3 got lost. Why do networks let bad things happen to good packets? That's what I really want to know. But so far, no one really knows anything has gone wrong. So everybody keeps operating like usual. Sender generates more packets. Receiver receives a packet. And now it knows something's wrong. It was expecting packet 3. It got packet 4. It generates a negative acknowledgement packet, and it sends the negative acknowledgement packet on the network. It puts packet 4 in the buffer. It leaves a hole for packet 3. The neck's going to take a while to arrive, though, so the sender's going to keep operating like normal, and the receiver's going to keep receiving some of these later packets. And then the sender gets the neck. It sees the receiver missed packet 3, but hey, it saved all of these packets in its buffer. So the sender resends packet 3. And the sender keeps generating packets. Receiver receives packets. The sender's buffer is now full. Packet 1 gets pushed out. That goes in the garbage. Receiver receives. Receiver finally gets packet 3. It fills it in the hole it left. And the process continues like normal. The receiver's buffer finally fills. And it plays out packet 1 to its TS demuxer and its decoders. So I mentioned these NAC packets before, and this is the representation of the NAC in the protocol overview. And it's a little bit confusing in this format. There's the SRT header. It starts with a 1 because it's a control packet, and then it's got this loss list thing. And what they're trying to say here is each loss list contains 1 or more entries, and each entry is either a single packet or a range. So you can say, I lost packets 5 and 9 and 11 through 15 all in one message. Besides negative acknowledgement, SRT does actually have positive acknowledgement. The receiver sends an acknowledgement every 10 milliseconds, and upon receiving an acknowledgement, the sender acknowledges that acknowledgement immediately. You can estimate round trip time based on this. And if you're at a high enough data rate that you have more than 64 packets between acknowledgements, the receiver sends a lightweight acknowledgement. This acknowledgement doesn't get re-acknowledged, and it doesn't contain the sort of metadata that an acknowledgement does. Now, this RTT thing is a little bit weird because there doesn't seem to be a way to resize the latency buffer without starting a new broadcast. So you can use it in the future, but its utility in the current broadcast is somewhat limited. So the acknowledgement and acknowledgement of acknowledgement packets are shown here. In the acknowledgement packet, the most important thing is the packet sequence number of the last packet received. And then there is the round trip time and the variance on the round trip time and some sort of buffering statistics, available buffer size in packets, packet receive rate, data receive rate. In a lightweight acknowledgement, you just get the sequence number. And the acknowledgement of the acknowledgement just tells you which acknowledgement it's acknowledging so you know what timestamps to subtract. So handshakes. Handshakes are always very simple. So in this GIF, Bill Maher keeps misreading Snoop, and Snoop keeps adapting on the fly to what Bill is doing. And this, I think, is a really good metaphor for how the SRT handshake works. So SRT actually has 4 handshakes. It has sender and receiver handshakes. There's the version 4 handshake and the version 5 handshake. And then it has something called the rendezvous handshake, where no party is designated sender up front. It's sort of a hand wave type protocol. It's really cool, but I'm not going to get into it in this talk. The big difference between version 4 and version 5 is the number of packets exchanged. In version 4, it's 4 round trips, and in version 5, it's just 2. So here are the layouts of the packets. I don't actually expect you to read all of this, but the core idea is I have version 4 on the left and version 5 on the right. Version 4 starts off with sort of an unmodified, not sort of, exactly an unmodified UDP handshake packet. And then it follows up with an SRT handshake packet that includes the latency it wants and the initial sequence number. And then after that, it does the keying material packet, which sets up the encryption for the data payloads. And in version 5, you just sort of take all these messages and kind of smush them together into one packet. So here's how it actually plays out in practice. For two parties attempting a version 5 handshake, the initiator creates a handshake induction packet, which means I want to start a handshake. It sets the version to 4, and there's this cookie field that it leaves unset. So the responder sees that it received an induction packet. It creates an induction packet. It sets the version to 5, and it sets a value to this cookie. It's going to want the initiator to come back with this cookie in a short period of time. It allows sort of the responder to not have to deal with people just spraying packets at it. You actually need to at least parse its packet to send something back. So a version 4 initiator would, at this point, ignore that version 5 and just keep filling in version 4 here and repeat the cookie and send the conclusion. But this initiator actually speaks version 5. So it's going to fill in version 5 in the version field, and it's going to fill out the SRT handshake extension values, including the latency. It's going to potentially fill in something called the stream ID, which I'll get to in a minute. And it fills in the crypto handshake as well. And the responder responds in kind with its latency value and its crypto handshake. So the stream ID I mentioned, this is an optional identifier sent in the second packet of the handshake, and the first one's meant to be discarded. So this is about as early as you can get. It's an application-specific parameter to tell you what the initiator wants. Am I trying to broadcast on a particular channel? Is there a resource I want you to play back to me? That kind of thing. And this contrasts with what RTMP does, where you do a TCP handshake, and then you do an RTMP handshake, and then you play bandwidth estimation, and then you call a bunch of esoteric RPCs to set up RTMP media streams, and then the person who called you tells you what the heck they actually want. So encryption, I mentioned before, SRT does not use DTLS. It uses industry standard primitives in a custom manner. It seems to be pretty heavily influenced by DVB scrambling. DVB is a European broadcast standard. The keying material is generated by a shared passphrase, and because of these retransmits, and because it uses key rotation, there's two keys valid at a time. You have an even key and an odd key, and you alternate which one you're updating. So if you're getting a retransmit, you can refer back to the old key. So this weird little note in the spec that says, hey, you know, encrypting whole packets seems like the most secure thing you can do, but actually encrypting headers is really bad from a brute forcing standpoint, and it particularly calls out the MPEG-TS sync byte. And sort of what you might, the initial gist you might get from this is that it wants you to not encrypt those TS sync bytes for the TS headers. But actually what it's saying is that instead we're just going to try to do key rotation really fast to make up for this. And you can see this if you like Wireshark a packet. We have a data packet here. It is encrypted. And if we look at the payload here, that first byte is 12 in hex, and maybe some of you know that if it were an unencrypted TS sync byte, it would be 47 in hex. So that's really all that I have today. If you want to learn more about the protocol, the SRT GitHub repository is probably your best bet, with the technical overview as a great supplemental tool, and Wireshark has a really great SRT dissector. And if you want to learn more sort of about the SRT ecosystem, what products and companies are involved in SRT, srtalliance.org. Yeah, I mean, it's definitely designed as an ingest protocol and as this one-to-one protocol and not doing some things you would want to do in delivery protocols. But there's no reason why you couldn't take this sort of the SRT datagrams and rather than running them over UDP, run them over something like WebRTC datagrams. So there is some potential there, but that's really not the problem they're trying to solve. All right, so there's a few different things. Number one, Nick, you seem to have positioned yourself into protocol. So yes, you need to do this to be good at your job. But more broadly, really, RIST and WebRTC even use a lot of the same tricks. And the industry is headed somewhere in this direction. Will it be SRT? Will it be WebRTC ingest? I don't really know. But you're sort of going to have to be comfortable with some of these fundamentals, I think, regardless. RTMP is dead. RTMP doesn't seem to be coming back at all right now. So if the no acknowledgement gets lost, presumably there's some burst of loss, so you're going to get some other packets that are lost. If acknowledgements get lost, the sender will actually start preemptively resending things. And if the receiver has not seen the packet that it was expecting by the time there's more loss, it will fill that into the loss list. It can essentially ride along for free with your next packet loss report. So there isn't like explicitly a jitter buffer. You have this whole latency buffer in the protocol that kind of fills that function. I'm not sure what the library sets to the default value, but what they recommend is about 2.5 round trips.